Find somewhere comfortable, somewhere your body can be heavy tonight if it wants to be. You don't need to follow any of this closely. You don't need to remember a single word. Just let the ideas arrive the way distant sounds do, present for a moment, then drifting on. We are in no hurry. The night is long and patient, and so are we. If today was hard, you can put it down now. Whatever you carried through the hours since morning, the small worries, the unfinished things, the quiet weight of being a person in the world, none of it needs to come with you into this. The dark is good for setting things down. Tonight, we are going to spend some time with one of the strangest and most beautiful ideas that human beings have ever discovered. It comes from physics, from the very small, from the world beneath the world we can see and touch. But it is not cold or abstract. It is, in its own quiet way, one of the most poetic things that science has ever found to be true. The idea is this, that at the deepest level of reality, things do not have fixed, definite properties until something forces them to settle. A particle, an electron, a photon of light, does not sit in one place or spin in one direction, waiting for us to look. It exists, genuinely and fully, across a whole landscape of possibilities at once. It holds every option open. It is, in the most literal sense that physics allows, many things at the same time. And then something looks, and it becomes one. We will take our time with this. We will follow it gently, from its earliest experimental hints, through the mathematics that gives it shape, into the thought experiments that have puzzled the greatest minds of the last 100 years, and out the other side into the laboratories of today, where physicists are doing things with this idea that would have seemed like pure imagination even a decade ago. You don't need to concentrate. You don't need to take notes. Just rest and let the words come and go, and somewhere in the spaces between them, something may settle into understanding all on its own. We begin with a coin. Picture a coin spinning in the air, not a coin that has been tossed and is on its way down, a coin that spins and never lands. It catches the light on one side and then the other, heads and tails flickering past so quickly that they blur into something that is neither one nor the other, and yet somehow both. That image is an old way of describing quantum superposition, and it is useful precisely because it breaks down at exactly the right moment. Because here is the thing, the spinning coin is still, at every instant, either heads or tails. It is moving too fast for us to see which, but if we could freeze time and look, we would find a definite answer. The coin is not genuinely both, it is one or the other, and our uncertainty is simply a failure of observation. A quantum particle is different, and the difference is not a matter of degree. It is not that the particle moves too quickly for us to catch. It is that, in a deep and mathematically rigorous sense, there is no definite answer to catch. The particle is not secretly one thing while we fail to notice which. It is genuinely, physically, both or all of its possible states at once. To understand how physics arrived at this conclusion, it helps to understand what physicists mean when they talk about a quantum state. When we describe an everyday object, a chair, a marble, a breath of air, we describe it in terms of definite properties. The marble is here, moving in that direction, at this speed. Every property has a single, specific value. This is the world as common sense imagines it. This is the world as Isaac Newton described it, and for the objects we can hold and see and measure with a ruler, it works beautifully. But when physicists began probing the worlds of electrons and photons in the early decades of the 20th century, they found that this picture quietly falls apart. An electron has a property called spin, a kind of intrinsic rotation, though not quite like the spinning of a top. Spin can be measured in two ways, either up or down along whatever axis you choose to measure it. And here is the remarkable thing. Before you measure it, the electron does not have a spin of up or a spin of down. It has a spin that is some combination of both. weighted in certain proportions, genuinely coexisting within the same particle. This is what superposition means, not ignorance, not hidden information, genuine, simultaneous multiplicity. The mathematical object that captures this is called the wave function. It was introduced in a form we still use today by the Austrian physicist Erwin Schrödinger in 1926, and it is one of the most important pieces of mathematics in all of science. The wave function is not a description of where a particle is or what it is doing. It is a description of everything the particle might be. A complete catalogue of possibilities, each one weighted by a number that tells you how likely that possibility is to be found if a measurement is made. Think of it less like a photograph and more like a weather map. A weather map does not tell you that it is raining in one place. It tells you that there is a 40% chance of rain here, a 70% chance there, clear skies somewhere else. The wave function is like that, except it is not describing our uncertainty about an already settled reality. It is describing the reality itself before it has settled. And crucially, the wave function is not just a list of probabilities sitting side by side. The different possibilities within it can interact with each other. They can reinforce one another, or they can cancel each other out, the way ripples on a pond either add together to make a larger wave or meet each other going in opposite directions and flatten into stillness. This interaction between possibilities, this interference, as physicists call it, is the thing that makes superposition genuinely different from ordinary uncertainty, and it has consequences that are visible in experiments, measurable, undeniable. There is a distinction worth dwelling on because it is easy to slide past it. Imagine you put a marble in a box, shake the box, close your eyes, and then reach in. You do not know which side of the box the marble is on, but the marble is on one side. Your ignorance does not change the marble's reality. A quantum particle is not like this. It is not that the particle is on one side and we simply do not know which. The particle's wave function genuinely spreads across both sides. It is in a superposition of positions. The interference effects that superposition produces are measurable. They would not exist if the particle were simply in one definite state that we had not yet determined. This is the heart of the thing. The universe, at its deepest layer, does not commit. It holds its options open with a kind of mathematical patience, keeping every possibility alive, weighted and ready, until the moment something forces a resolution. There is something quietly extraordinary in that. We are used to thinking of reality as a collection of settled facts, things that are what they are, independent of whether anyone is looking, and at the scale of everyday life, that picture is accurate enough. But beneath it, at the level of the particles that make up everything we can see and touch, reality is softer than that, more flexible, more provisional. The universe, it turns out, prefers to keep its options open. And the story of how we know this begins with a beam of light passing through two narrow slits in a piece of card. In the year 1801, a British physician and natural philosopher named Thomas Young set up one of the most important experiments in the history of science, and he did it with equipment that would not have looked out of place in a school classroom. He took a source of light, a piece of card with two narrow slits cut into it, and a screen to catch whatever came through. He shone the light at the card, and what appeared on the screen was not what you would expect. If light were made of tiny particles, little bullets of brightness, you would expect to see two bright bands on the screen, one behind each slit, where the particles flew straight through. But that is not what appeared. What appeared was a series of alternating bright and dark stripes spread across the screen in a regular, repeating pattern. Many bright bands, many dark bands, fanning out from the center. This is called an interference pattern, and it is the signature of waves. To understand why, think of dropping two stones into a still pond at the same time, a short distance apart. Each stone sends out circular ripples. As those ripples spread, they meet each other. Where the peak of one ripple meets the peak of another, they add together and make a taller wave. This is called constructive interference. Where the peak of one meets the trough of another, they cancel each other out and the surface goes flat. This is called destructive interference. The result is a complex, beautiful pattern of regions where the water is very disturbed and regions where it is almost still. Young's experiment showed that light does exactly this. The two slits acted like two stones dropped into the pond. Light waves spread out from each slit, met each other, and where they reinforced, a bright band appeared on the screen. Where they cancelled, a dark band appeared. The pattern was unmistakable. For about a century, that was more or less where things stood. Light was a wave. A beautiful, mathematically well-described wave, later understood to be a wave of oscillating electric and magnetic fields, moving through space at about 300 million meters per second. But then, in the early 20th century, physics began to complicate this picture in ways that nobody expected. Max Planck and Albert Einstein showed that light also comes in discrete packets, individual chunks of energy that Einstein called photons. Light is a wave, and it is also made of particles. This is called wave-particle duality, and it was deeply unsettling to the physicists who had to accept it. And then things got stranger still. In 1927, two American physicists named Quentin Davison and Lester Germer were working at Bell Labs in New York, firing electrons, particles with actual mass, actual substance, at a crystal of nickel. The crystal's regular atomic structure acted like a diffraction grating, and what they found in the scattered electrons was an interference pattern. Not the pattern you would expect from particles bouncing off a surface. A wave pattern. A pattern that said, unmistakably, that electrons were behaving like waves. At almost the same moment, in Britain, a physicist named George Paget Thomson was doing a similar experiment, firing electrons through thin metal foils and finding the same thing. Both sets of researchers were awarded the Nobel Prize. Electrons, things with mass, things that can be deflected by electric and magnetic fields, things that carry charge, were also waves. The double-slit experiment was then performed with electrons, and what it revealed was the thing that physicists have been quietly astonished by ever since. Here is the setup. A source of electrons, firing them one at a time. Not a stream, not a beam, but individual electrons, separated by enough time that only one is ever in the apparatus at once. A barrier with two slits. A detector screen that records where each electron lands, building up a picture dot by dot as they arrive. If electrons were simply particles, you would expect the dots to cluster into two bands, one behind each slit, the way bullets cluster behind two holes in a wall. Each electron, you might assume, goes through one slit or the other, lands somewhere on the screen, and the next electron does the same. But that is not what happens. One by one, the electrons arrive on the screen, one here, one there. The pattern seems random at first, the dots scattered without obvious structure. But as more and more electrons arrive, hundreds, then thousands, then tens of thousands, a pattern emerges from the randomness. Not two bands, an interference pattern. The same alternating stripes of many and few that Young saw with his light, now built up one electron at a time. Think about what this means. Each electron was sent alone. There was no other electron for it to interfere with, and yet the pattern it helped to create was the pattern of interference. The only way to account for this is to say that each individual electron somehow passed through both slits at once, that its wave function spread through both openings simultaneously, that the two parts of its wave function overlapped and interfered with each other on the other side, and that this interference determined where the electron was likely to land. The electron did not choose slit 1 or slit 2. It went through both. It was in a superposition of two paths. Now, Physicists being physicists, the natural response to this was to ask, well, can we just check? Can we put a detector at the slits and see which one the electron actually goes through? Yes, you can do this. You can place a detector at each slit that registers the passage of an electron without stopping it, a gentle interaction, just enough to tell you which path the electron took. And when you do, the interference pattern vanishes. Not weakens, not blurs slightly, vanishes entirely. The dots on the screen rearrange themselves into two simple bands, one behind each slit, exactly as you would expect from ordinary particles going through one opening or the other. The moment you determine which path the electron took, it stops behaving as though it took both. This is the measurement problem in its most visceral form, the act of gathering information, of asking the universe a question and insisting on an answer. Changes the result. The electron, forced to declare which slit it passed through, gives up its superposition of paths. It becomes a particle again in the ordinary sense. The wave function, which had spread through both slits and interfered with itself, collapses into a single definite trajectory. The interference pattern was the fingerprint of superposition. Its disappearance upon measurement is the fingerprint of collapse. And between these two things, the pattern that builds when no one is watching and the pattern that vanishes when someone is, lies the deepest mystery in all of physics. It is worth sitting with the image for a moment. Thousands of electrons, each one alone in the apparatus, each one somehow passing through two openings at once, each one interfering with itself, each one landing in a place determined not by a single definite path, but by the overlap of two possible paths, and collectively, patiently, building up a picture of stripes on a screen. The pattern does not exist in any one electron. It exists in the mathematics of the wave function, in the quiet arithmetic of superposition, in the universe's refusal to commit until something asks. It is one of the most carefully verified results in all of science, and it remains, in a certain light, completely astonishing. The double-slit experiment tells us that superposition is real. But to understand what superposition actually is, what it is made of, how it works, why it behaves the way it does, we need to go a layer deeper into the mathematics that describes it. And this is worth doing carefully, because the mathematics is not just a tool for calculation. It is, in a very real sense, the closest thing we have to a description of what is actually happening. The wave function, which we have already met, is the central object. It is usually written using the Greek letter psi, and it is a function, meaning it has a value at every point in space and at every moment in time. But the values it takes are not ordinary numbers. They are complex numbers, meaning they have two components, a real part and an imaginary part. This is not a quirk of mathematical notation. The two-component nature of these numbers is what allows the wave function to encode the phase of a quantum state, the information about where a wave is in its cycle of peaks and troughs, and it is this phase information that makes interference possible. Here is the key idea. When a particle is in a superposition of two possible states, say spin up and spin down, or path through slit 1 and path through slit 2, its wave function is a combination of the wave functions for each individual state. The two-component wave functions are added together, weighted by numbers called probability amplitudes. Each probability amplitude is a complex number, and its magnitude, how large it is, ignoring its direction in the complex plane, tells you something important. When you square that magnitude, you get the probability of finding the particle in that particular state if you were to make a measurement. So, if a particle is in a superposition of spin up and spin down with probability amplitudes of equal size, then squaring those amplitudes gives equal probabilities for each outcome. 50% chance of measuring spin up, 50% chance of measuring spin down. But the particle is not 50% one thing and 50% another in some physical sense, the way a coin might be half painted red. It is genuinely both, with the full wave function encoding both possibilities at once. And here is the crucial difference from ordinary probability. With ordinary probability, the probabilities of different outcomes simply add together. If you flip a coin twice, the probability of 2 heads is a quarter, and you get that by multiplying the individual probabilities. And because amplitudes are complex numbers with phases, they can cancel each other out before you square them. This cancellation is interference. It is the thing that makes certain outcomes impossible, the dark bands in the double slit pattern, not because the particle is blocked, but because the 2 paths through the apparatus produce amplitudes that point in opposite directions and annihilate each other. This is the mathematical heart of why superposition is different from ordinary uncertainty. With ordinary uncertainty, all the possible outcomes are still possible. They just have different probabilities. With superposition, the interaction between amplitudes can make some outcomes completely forbidden, driving their probability to 0. This is not something that can happen if the particle is simply in one unknown definite state. It requires the particle to be genuinely in multiple states at once, with those states interfering. Now, why does superposition exist at all? Why does the universe permit particles to be in multiple states simultaneously, rather than simply being in one state or another? The answer lies in the nature of the equation that governs how quantum systems evolve over time. Schrödinger's equation, developed in 1926, describes how the wave function changes from moment to moment. It is a differential equation, a mathematical statement about rates of change, and it has a property called linearity. Linearity means, roughly, that if you have 2 valid solutions to the equation, then any combination of those solutions is also a valid solution. If spin up is a valid quantum state, and spin down is a valid quantum state, then spin up plus spin down, in any proportions, is also a valid quantum state. The equation does not forbid combinations. It demands that combinations be allowed. This is not a trivial statement. Many equations in physics are not linear, and for those equations you cannot simply add solutions together. But the Schrödinger equation is linear, and this linearity is not an accident or an approximation. It appears to be a fundamental feature of the quantum world. And its direct consequence is superposition. Because if the equation allows combinations, and because the wave function obeys the equation, then the wave function can be a combination, always. Inevitably, the mathematics insists on it. There is something quietly profound in this. Superposition is not a strange exception to the rules of quantum mechanics. It is not an edge case or an anomaly. It follows directly, necessarily, from the most fundamental equation we have for how quantum systems behave. The universe permits particles to hold multiple states at once because the equation governing their evolution is linear, and that linearity appears to go all the way down. It is worth pausing on what the wave function is not. It is not a physical wave rippling through space, the way a water wave ripples through the ocean. There is no medium it travels through. It does not carry energy from place to place. It is, instead, a mathematical object that lives in an abstract space of all possible configurations of the system it describes, a space that grows enormously in size as the system becomes more complex. For a single particle moving in one dimension, the wave function is a relatively simple thing. For a system of 2 particles, it already lives in a space of 6 dimensions. For a system of many particles, it becomes something of extraordinary complexity, encoding all the correlations and relationships between them. What the wave function represents, at its most honest, is a complete description of everything we could possibly know about a quantum system and everything the system could possibly be. It is the universe's own accounting of its open possibilities, patient, precise, and held in a kind of mathematical suspension until the moment something reaches in and asks, The image that stays with me thinking about the wave function is of a landscape seen in the last of the evening light. Not dark yet, but fading. Every hill and valley still present, but soft, their edges indistinct. The landscape is real. It is all there. But the sharp definitions of daylight have not yet arrived, and in that gentle ambiguity, everything is still possible. That is the wave function. Everything still possible. Waiting, unhurried, for the question that will make it choose. If superposition is real, if particles genuinely exist in multiple states at once, then what happens when we look? What is the mechanism by which a particle in a superposition of many possibilities becomes, in the instant of measurement, a single definite thing? This question is called the measurement problem, and it is, without exaggeration, one of the deepest unsolved problems in all of science. Not because physicists cannot calculate the right answers, they can with extraordinary precision, but because no one fully agrees on what those calculations are telling us about the nature of reality. Let us start with what we know happens before worrying about why. When a quantum system interacts with a measuring device, or more broadly, with any system large enough to be described as classical, the superposition of the quantum system appears to resolve. The wave function, which encoded all the possible outcomes weighted by their probability amplitudes, seems to collapse into a single outcome. If the electron's spin was in a superposition of up and down, and you measure it, you get either up or down, never both. The probability of each outcome is given by squaring the corresponding amplitude exactly as the mathematics predicted. And after the measurement, the electron is in a definite state, the one you found. This transition from the smooth, continuous, linear evolution of the wave function to the sudden, irreversible selection of a single outcome is called wave function collapse. And it is deeply puzzling for reasons that become clear the moment you look at it carefully. The Schrodinger equation, as we have established, is linear. Its solutions can be combined. It evolves the wave function continuously and smoothly without ever selecting one outcome over another. There is nothing in the Schrodinger equation that corresponds to collapse. Collapse appears to be a different kind of process, discontinuous, irreversible, and not described by the same equation that governs everything else. And yet it seems to be exactly what happens when we measure. This tension was already apparent to the physicists who built quantum mechanics in the 1920s, and it troubled them deeply. In 1935, Erwin Schrödinger, the same man who wrote the equation, devised a thought experiment specifically to dramatize how troubling it was. He imagined a cat placed inside a sealed box. Inside the box, along with the cat, is a small amount of radioactive material, just enough that there is a 50% probability of one atom decaying within the next hour. Connected to the radioactive material is a Geiger counter, a device that detects radioactive decay. And connected to the Geiger counter is a mechanism that, if the Geiger counter fires, will release a vial of poison gas, killing the cat. Now, according to the Copenhagen interpretation, the most widely accepted view of quantum mechanics at the time, developed primarily by Niels Bohr and Werner Heisenberg, a quantum system remains in superposition until it is measured. The radioactive atom, unobserved inside the box, is in a superposition of decayed and undecayed. Its wave function contains both possibilities, each with a probability amplitude. But the Geiger counter is connected to the atom, and the poison mechanism is connected to the Geiger counter, and the cat is connected to all of it. If the atom is in a superposition, then so is the Geiger counter, both fired and not fired, and so is the poison mechanism, both triggered and not triggered, and so, by the same logic, is the cat. The cat, according to the Copenhagen interpretation applied consistently, is in a superposition of alive and dead. Schrödinger did not propose this because he believed it. He proposed it as a reductio ad absurdum. a demonstration that something must be wrong with how we are thinking about superposition. He found the idea, in his own words, quite ridiculous. A cat, he felt, was simply not the kind of thing that could be both alive and dead at once, and if the mathematics led to that conclusion, then something in the mathematics, or in our interpretation of it, needed fixing. The thought experiment has been at the center of debates about quantum mechanics ever since, and different physicists have responded to it in very different ways. The Copenhagen interpretation, in its most pragmatic form, sidesteps the paradox by drawing a firm line between the quantum world and the classical world. Quantum systems evolve as superpositions. Classical systems, measuring devices, cats, observers, do not. The wave function collapses at the boundary between them. The cat is classical. When the box is opened, the cat is found to be either alive or dead, because cats are classical objects and the act of looking is a classical measurement. The paradox on this view arises from trying to apply quantum mechanics to things it was never meant to apply to. But this answer is deeply unsatisfying to many physicists because it introduces a fundamental division, quantum versus classical, without ever explaining where that boundary is or why it exists. The cat is made of atoms. The Copenhagen interpretation does not say. A very different response came from an American physicist named Hugh Everett III, who proposed his interpretation in 1957. Everett took the Schrodinger equation completely seriously, with no collapse, no boundary, no special role for observers. Instead, the measuring device becomes entangled with the quantum system. It enters a superposition in which it has recorded spin up and recorded spin down simultaneously, and then the observer who reads the measuring device becomes entangled too, entering a superposition in which they have seen spin up and seen spin down. The entire universe, on this view, evolves as a vast branching superposition, with every possible outcome of every quantum measurement occurring in some branch. This is the many worlds interpretation, and it has the considerable virtue of requiring no special collapse mechanism and no arbitrary quantum classical boundary. But it comes at a cost. It implies that reality is unimaginably vaster than it appears, that every quantum event spawns new branches of a universal wave function, that somewhere in this branching structure there is a version of you in which everything that could have happened to you today did happen to you, in its own branch. A third approach, which has gained significant traction in recent decades, is the decoherence picture. Decoherence, which we will explore in much more depth in the next chapter, describes how a quantum system loses its superposition through interaction with its environment. Every stray photon, every vibrating atom in the surrounding air, every faint electromagnetic fluctuation is constantly interacting with the quantum system and becoming entangled with it. As this happens, the delicate phase relationships between the different components of the superposition, the relationships that make interference possible, become scrambled and effectively invisible. The superposition does not collapse in some metaphysically dramatic sense. It simply becomes impossible to observe because the information about the phase relationships has spread into billions of environmental particles and cannot be recovered. Decoherence explains, very convincingly, why we never see quantum superpositions in everyday life. It explains why cats do not appear to be both alive and dead, but it does not, by itself, fully solve the measurement problem. It explains why we cannot see the interference between the alive cat branch and the dead cat branch. It does not explain why, when we open the box, we find ourselves in only one of them. This is where physicists still genuinely disagree. The measurement problem is not resolved. The different interpretations, Copenhagen, many worlds, decoherence combined with various other ideas and several others besides, each capture something important and each leave something unexplained. The debate is not merely philosophical. It bears on questions about the nature of probability, the role of observers, and what it even means to say that something is real. And perhaps there is a kind of comfort in that. The greatest minds that physics has ever produced have looked at this problem and found it genuinely hard. Not because they were not clever enough, but because the question sits at the very edge of what science can currently say. The universe holds its mystery here with the same patience it holds everything else. The cat in the box remains, in some sense, a question that the universe has not yet fully answered. If superposition is the universe's deepest tendency, its preference for holding all options open, then why do we never see it in daily life? Why is the chair in the corner of the room firmly in one place and not in a superposition of 10,000 positions? Why does a glass of water not exist in a shimmering cloud of possible temperatures? Why does everything around us appear so stubbornly, reassuringly definite? The answer has a name: decoherence, and understanding it requires understanding what coherence is in the first place. When a particle is in a superposition of two states, the wave function that describes it contains both states at once, combined with specific phase relationships between them. Phase, here, refers to the relative timing of the oscillations in the wave function, whether the two component waves are in step with each other, out of step, or somewhere in between. It is this precise phase relationship that makes interference possible. When the phases are aligned correctly, the two parts of the superposition can reinforce or cancel in the specific ways that produce interference patterns. When the phase relationship is preserved, the superposition is coherent. It can still interfere, still produce quantum effects, still be in a genuine superposition in the observable sense. Decoherence is what happens when that phase relationship is disrupted. And it happens through interaction with the environment, not dramatic interaction, not a measurement in the laboratory sense, not a physicist with a detector, just the ordinary, constant, unavoidable contact between a quantum system and the sea of particles surrounding it, a photon of light bouncing off the system, a molecule of air grazing it, a faint vibration transmitted through the material it sits on. Each of these interactions is a tiny entanglement. The state of the environment becomes correlated with the state of the quantum system. And as the environment becomes entangled with the quantum system, the phase information that made the superposition coherent becomes distributed across an enormous number of environmental particles, effectively diluted into noise. What this means concretely is that the interference effects disappear. Not because the superposition has literally collapsed in some dramatic sense, but because the information needed to observe the interference has leaked away into the environment and cannot be recovered. The different components of the superposition can no longer interfere with each other because their relative phases are scrambled. From the outside, the system looks as though it has settled into one definite state, but according to the mathematics, the superposition is still there. It has simply become entangled with so many environmental particles that it is, for all practical purposes, invisible. The timescale on which this happens is extraordinary. For a large object in a warm, dense environment, say a dust particle floating in air at room temperature, the timescale for decoherence is around 10 to the power of minus 31 seconds. That is 100 million, trillion times faster than the blink of an eye. It is so fast that it is essentially instantaneous by any measure we could apply. The dust particle never has a chance to display quantum behavior because the environment destroys its coherence before any quantum effect could become observable. For smaller and more isolated systems, the timescale is longer but still challenging. For a single molecule in a relatively clean environment, coherence might persist for femtoseconds, a femtosecond being 1/millionth of a billionth of a second. For carefully isolated atoms in a laboratory, it can be extended to microseconds or even milliseconds. And for qubits in the most advanced quantum computing systems today, researchers have pushed coherence times into the range of seconds, an extraordinary achievement that required decades of engineering. This is why the quantum world stays hidden. Every object around you is constantly, incessantly bombarded by photons of light, by molecules of air, by thermal vibrations transmitted through whatever it sits on. Each of these interactions is a tiny decoherence event, each one spreading the phase information of any superposition into the environment, each one contributing to the relentless process by which quantum possibilities are resolved into classical facts. To see a chair in a superposition of positions, you would need to isolate it from every photon, every air molecule, every vibration, every electromagnetic fluctuation, every thermal fluctuation, from everything, essentially, and cool it too, within a tiny fraction of a degree of absolute zero, which is minus 273 degrees Celsius, the coldest temperature that physics permits. Even then, the chair contains so many atoms, each of which interacts with its neighbors, that internal decoherence would destroy the superposition almost immediately. This is why quantum effects are confined in ordinary life to the very small and the very cold. Not because quantum mechanics stops applying at some size threshold, there is no evidence that it does, but because decoherence is so efficient at larger scales that the quantum behavior is washed away before it can be seen. And this is why maintaining superposition in a laboratory is such an extraordinary technical challenge. To preserve the coherence of a quantum system long enough to study it or use it, physicists must create conditions of almost unimaginable stillness and isolation. Quantum computing experiments are performed in dilution refrigerators, devices that cool their contents to temperatures around 10 mK, which is about 10,000ths of a degree above absolute zero, colder than the average temperature of deep space. The systems are shielded from electromagnetic interference by layers of superconducting material. Everything that might carry information about the quantum state away into the environment must be suppressed. Even so, coherence times remain finite. Decoherence is not a problem that can be entirely solved, only managed, delayed, and worked around. There is a strange beauty in this picture. Superposition is not rare or exotic. It is, in a sense, the default condition of every particle in the universe. Every electron, every photon, every atom is constantly in a superposition of something. Position, momentum, spin, energy. The quantum world is everywhere, all the time, underlying everything. But it is also extraordinarily fragile. The moment the world pays attention, the moment any environmental particle becomes entangled with a quantum system, the coherence begins to dissolve, the interference fades, and the classical world reasserts itself. Superposition is ancient and ubiquitous and perpetually present, and it vanishes, silently and instantly, the moment anything notices it is there. For most of the 20th century, quantum superposition was understood to be a property of the very small. Electrons, photons, individual atoms. These were the objects that lived in the quantum world. The classical world, the world of things you could see and touch, began somewhere above that scale, and the line between them, while philosophically undefined, seemed practically clear enough. Nobody expected to see a pebble in two places at once. But in recent years, physicists have been quietly, methodically pushing that boundary, and what they have found is that the boundary is not where anyone thought it was. To understand what these experiments involve, it helps to understand how physicists actually demonstrate that something is in a superposition. The key tool is interference. If an object passes through an apparatus as a wave, as a superposition of multiple paths, then when the paths are recombined, they interfere with each other, and the resulting distribution of arrival positions shows the characteristic banding of an interference pattern. If the object were simply a particle following one definite path, no such pattern would appear. The interference pattern is the proof. It is the fingerprint of superposition. The apparatus used to produce this pattern is called an interferometer. In its simplest form, an interferometer takes a quantum object, splits it along two possible paths using some kind of beam splitter, a device that puts the object into a superposition of going left and going right, allows the two paths to travel separately for some distance, and then recombines them. If the object maintained its superposition throughout, if its coherence was not destroyed by environmental interaction, the two paths interfere when they meet, and the pattern of where objects arrive at the detector reveals the interference. If coherence was lost at any point, the pattern disappears. For individual atoms and small molecules, this kind of experiment has been routine for decades. The challenge has always been to scale it up, to demonstrate interference and therefore superposition in progressively larger and more massive objects, pushing back against decoherence at every step. In February 2026, a team of researchers at the University of Vienna and the University of Duisburg-Essen published a result in the journal Nature that marked a genuine milestone. Tiny clusters of sodium atoms, each cluster containing around 7,000 atoms, cooled them to extraordinarily low temperatures and sent them through an interferometer. What they observed on the detector was a clear interference pattern, an unmistakable, repeatable, statistically robust interference pattern, built up from the arrival of individual nanoparticles, each one having passed through the apparatus as a wave. 7,000 atoms, moving as one, in a superposition of two paths simultaneously. To appreciate how extraordinary this is, consider the scale. A single sodium atom has a diameter of roughly 370 picometers, about 370 trillionths of a meter. A cluster of 7,000 of them is still, by any everyday measure, invisibly small. But in the world of quantum mechanics, it is enormous. It is a macroscopic object in quantum disguise, and the fact that it can maintain coherence long enough to produce an interference pattern means that decoherence, the great enemy of superposition, was held at bay through careful cooling and isolation long enough for the quantum behavior to become visible. The cooling is essential. At room temperature, the thermal energy of the particles, the energy of their random vibrations, is more than enough to destroy coherence almost instantly. By cooling the nanoparticles to temperatures approaching absolute zero, the researchers reduced this thermal noise to the point where coherence could persist for long enough to traverse the interferometer. The isolation is equally important. Any stray photon, any residual gas molecule in the vacuum chamber, any vibration transmitted through the apparatus could entangle itself with the nanoparticle and destroy the superposition. The technical achievement is staggering. The vacuum chambers used in these experiments must maintain pressures billions of times lower than atmospheric pressure, conditions in which the density of air molecules is so low that a nanoparticle can travel centimeters without encountering a single one. The cryogenic systems that cool the particles require elaborate engineering to reach temperatures a fraction of a degree above absolute zero. The interferometer itself must be mechanically stable to within a fraction of the wavelength of light. Any vibration large enough to shift the apparatus by even a few nanometers would wash out the interference pattern. Around the same time, in May 2026, a team from the Southern University of Science and Technology in China published a related result in Nature Physics. They had created a cluster of 7 atoms, a different scale, but equally remarkable in its own way, and demonstrated that this cluster could enter a superposition state through a process called quantum tunneling. Quantum tunneling is the phenomenon by which a particle crosses a barrier that, according to classical physics, it should not have enough energy to cross. Imagine a ball rolling toward a hill. Classically, if the ball does not have enough energy to reach the top, it rolls back. But in quantum mechanics, the ball's wave function extends through the hill, and there is a genuine probability that the ball will appear on the other side, as though it passed through the barrier rather than over it. For this to happen with a 7-atom cluster is a significant extension of a phenomenon usually associated with individual particles. What both of these experiments tell us is something that physicists have suspected for some time, but are now demonstrating with increasing clarity. The boundary between the quantum world and the classical world is not a fixed line. It is not written into the laws of physics at some specific scale. It is instead a practical boundary set by the engineering challenge of isolating an object from its environment well enough and long enough for its quantum behavior to remain observable. This is a profound shift in perspective. For most of the 20th century, the quantum classical divide felt like a fundamental feature of nature, something built into the structure of reality. But the experimental evidence increasingly suggests otherwise. Objects composed of thousands of atoms can maintain quantum superpositions. The laws of quantum mechanics appear to apply at these scales, just as they do at the scale of a single electron. The reason we do not ordinarily see quantum behavior in large objects is not that quantum mechanics stops working. It is that decoherence is extraordinarily efficient in warm, noisy environments, and we live in one of those. There is a question that hangs over all of this work, and it is one that physicists are now beginning to feel they might be able to test. If superposition persists into the scale of thousands of atoms, how far does it go? Could a grain of sand be placed in a superposition of two positions? Could something you could see with your naked eye? The theoretical answer, as far as we can tell, is yes, provided you could isolate it sufficiently. The practical answer is that the engineering required becomes more extraordinary the larger the object. But the boundary, wherever it is, appears to be a matter of engineering rather than principle. And that is perhaps the most quietly astonishing thing that these experiments have revealed. Not just that nanoparticles can be in two places at once, but that the universe, as far as we can tell, does not draw a line. Everything we have explored so far, the wave function, the interference pattern, the careful isolation of nanoparticles from their environments, has been about understanding superposition, about revealing it, measuring it, marveling at it. But superposition is not only something to be observed, it is something that can be used. And the use that has attracted the most attention, the most investment, and the most astonishment is quantum computing. To understand why quantum computing is so fundamentally different from ordinary computing, it helps to start with what ordinary computing actually is. Every classical computer, every laptop, every phone, every server operates on bits. A bit is the simplest possible unit of information. It can be either 0 or 1, off or on, false or true. Everything a classical computer does, no matter how complex it appears, is ultimately a sequence of operations on strings of these two-valued digits. A single bit holds one piece of information. 8 bits hold a byte. A modern processor manipulates billions of bits per second, and the extraordinary complexity of modern software emerges from the sheer speed and scale of these simple operations. But a bit is always one thing, 0 or 1, never both. A qubit, a quantum bit, is different. A qubit is a quantum system that has two possible states, analogous to 0 and 1, but which can exist in a superposition of both simultaneously. The physical realization of a qubit varies. It might be the spin of an electron, which can be up or down. It might be the energy level of a superconducting circuit. It might be the polarization of a photon, but in every case, the key property is the same. Before measurement, the qubit is not in state 0 or state 1. It is in a superposition of both, with probability amplitudes for each. Now consider what this means for a system of multiple qubits. Two classical bits can be in one of four possible states, 0001, 10, or 11. At any given moment, a 2-bit classical system is in exactly one of these four states. Two qubits in superposition are in all four states simultaneously. The wave function of the 2-qubit system contains all four possibilities at once, each weighted by its probability amplitude. 3 qubits in superposition represent all 8 possible 3-bit strings simultaneously. 4 qubits represent 16. 10 qubits represent 1024. The number of states represented simultaneously doubles with every qubit added, growing exponentially. 300 qubits in superposition can represent more states simultaneously than there are atoms in the observable universe, a number so large that writing it out would require more digits than there are seconds since the Big Bang. This is the source of quantum computing's extraordinary potential. A quantum computer does not simply process information faster than a classical one. It processes information differently. It holds an exponentially large number of possible answers in superposition simultaneously, and it operates on all of them at once. But this immediately raises a question. If measuring a quantum system collapses its superposition to a single state, how do you get a useful answer out of a quantum computer? If you measure the qubits at the end of a calculation, you get one of the exponentially many possible outcomes chosen at random according to the probability amplitudes. That would not be useful. You need to get the right answer, not a random one. The solution is interference. A quantum algorithm is designed so that the probability amplitudes for wrong answers interfere destructively. They cancel each other out, driving their probabilities towards zero, while the amplitudes for correct answers interfere constructively, reinforcing each other and driving their probabilities toward 1. When you measure at the end, you get the right answer, not because the quantum computer checked all possibilities sequentially, but because it orchestrated the interference of amplitudes so that only the correct answer survives. This is a delicate and beautiful process. It requires the superposition to remain coherent throughout the entire calculation, because the interference only works if the phase relationships between the different components of the superposition are preserved. Any decoherence, any leakage of phase information into the environment disrupts the interference and corrupts the answer. This is why maintaining coherence in quantum computers is such a central engineering challenge, and why those dilution refrigerators and electromagnetic shields are necessary. The algorithms that exploit this most powerfully are designed for specific types of problems. One of the most famous, developed by the mathematician Peter Shor in 1994, can factor large numbers, find the prime factors of a very large integer, exponentially faster than any known classical algorithm. This matters because the security of most modern internet encryption rests on the assumption that factoring large numbers is computationally impractical. A sufficiently powerful quantum computer running Shor's algorithm could, in principle, break that encryption. This has driven enormous investment in quantum computing research and equally enormous investment in developing new forms of encryption that would be secure even against quantum computers. Another famous algorithm, developed by Lovegrover in 1996, provides a quadratic speedup for searching an unsorted database. If you have 1,000,000 items and you are looking for one specific item, a classical computer has to check up to 1,000,000 items in the worst case. Grover's algorithm, using superposition and interference, can find it in roughly 1,000 steps, the square root of 1,000,000. This speedup applies to a vast range of optimization and search problems. Quantum cryptography takes a different approach to security, not computing answers faster, but making eavesdropping physically detectable. The idea rests on the collapse of superposition upon measurement. If two people want to share a secret key, a string of random bits used to encrypt their messages, they can do so using quantum particles in superposition. Each particle is sent in a superposition of states, and the receiver measures it, collapsing the superposition. If an eavesdropper intercepts the particles and measures them to learn the key, the act of measurement collapses the superpositions and changes. When the sender and receiver compare a portion of their results, they can detect the statistical signature of this interference. The eavesdropper cannot listen in without leaving fingerprints. The security is not computational. It does not depend on any mathematical problem being hard to solve. In December 2024, researchers at Caltech announced a technique that brings superposition into the realm of chemical sensing. Using ultra-fast laser pulses lasting femtoseconds, each one a brief flash of light lasting a millionth of a billionth of a second, they created superpositions of electron spin states in relatively simple molecules. These superpositions are exquisitely sensitive to the chemical environment around the molecule. The precise way the superposition evolves over time depends on properties like the viscosity of the surrounding liquid, the presence of specific molecules nearby, or subtle changes in the local electromagnetic field. By measuring how the superposition evolves, tracking it with further laser pulses at precisely timed intervals, the researchers could read out information about the molecule's chemical surroundings with a sensitivity that classical measurement techniques cannot match. The same principle that makes a single electron in a physics laboratory seem so philosophically puzzling is now being shaped into tools that might one day help discover new medicines. By simulating the quantum behavior of drug molecules with an accuracy that classical computers cannot achieve. It is being shaped into sensors that can detect the faintest magnetic fields, with applications in brain imaging and geological surveying. It is being shaped into communication systems whose security is guaranteed not by mathematics but by the laws of physics themselves. The quantum world is no longer only a subject of wonder. It is becoming, gradually and with enormous difficulty, a resource. And the resource is superposition, the universe's deepest preference for holding every possibility open, now being harnessed carefully and ingeniously to do things that a world of fixed, definite states could never do. We have come a long way tonight, and the journey has been a quiet one. No urgency, no rush, just a slow, careful walk through one of the strangest and most beautiful ideas that human beings have ever managed to put into words. Let it all come back gently now, without effort. Not as a list, not as a summary, but the way images return when you are almost asleep, softly, one after another, already beginning to dissolve at the edges. The spinning coin that never lands, that was where we began. And we found that the coin was never quite the right image, because the coin, at every moment, is secretly one thing, even if we cannot see which. The quantum particle is something different, something more patient, more open, more genuinely undecided. It holds both possibilities, not as a temporary confusion, but as its actual physical reality. Both simultaneously. Neither one, both. Then the light through two doors, building its pattern of stripes on the screen. And the electrons, one at a time, each one alone in the dark of the apparatus, each one somehow passing through both openings at once and interfering with itself, building, particle by patient particle, a picture that could only exist if each one had been in two places at once. That pattern, accumulating in silence over hours, is one of the most quietly remarkable things that physics has ever asked us to accept, and the evidence demands that we accept it. Then the mathematics, the wave function, that patient landscape of possibilities, each one weighted by its amplitude, each amplitude carrying its phase, the phases interfering with each other in ways that make certain outcomes vanish and others become almost certain. Not a description of our ignorance, but a description of genuine, simultaneous, distributed reality. The Schrodinger equation, linear at its heart, permitting combinations, demanding that superposition be not just allowed but inevitable. Then the cat in the box. Schrödinger's pointed argument, his careful absurdity, his insistence that something in the picture must be wrong. And the three great responses to his challenge, the Copenhagen boundary between quantum and classical, the many worlds branching of everything that could happen into everything that does, and the decoherence picture in which the quantum bleeds into the environment and becomes invisible. None of them complete, all of them capturing something real. The mystery still open, still unresolved, still sitting quietly at the center of the deepest physics we have. Then decoherence itself, the great spoiler, the reason the quantum world stays hidden. The way a single stray photon, a single molecule of air, a single faint vibration can entangle itself with a quantum system and carry its phase information away into the environment, dissolving the coherence that made interference possible. The way this happens in a femtosecond in warm, dense matter, and why the world around us appears so stubbornly definite, so reassuringly classical, even though quantum mechanics underlies every atom of it. Then the nanoparticles, 7,000 sodium atoms, cooled to temperatures colder than deep space, sent through an interferometer in a laboratory in Vienna and producing, on the detector, a pattern of interference. The boundary between quantum and classical revealed to be not a wall, but a fog, not a principle, but an engineering challenge. The universe, as far as we can tell, draws no line. And then the qubits, holding their superpositions in dilution refrigerators, their probability amplitudes interfering to coax correct answers out of calculations that would take classical computers longer than the age of the universe. The same principle from the double-slit experiment to the quantum computer, from a single electron to a nanoparticle of 7,000 atoms. The universe holds every possibility open until it is asked. There is something in this that goes beyond physics, or perhaps it is more accurate to say that the physics illuminates something we already knew, but had not quite found the right words for. We live, most of the time, in a world of collapsed wave functions, a world of settled facts, definite positions, outcomes already chosen. The day fills up with certainties, things that happened, things that did not, the fixed contours of what is and what is not. There is a kind of weight to all of that, a heaviness that accumulates. By the time the night comes, the day has made so many demands on certainty, has insisted so many times on definite answers, that the body is tired with the effort of it. But beneath all of that, beneath every definite thing, every settled fact, every outcome that has already been chosen, the wave function is still there. The quantum world is still running, patient and unhurried, holding its options open at the level of every atom in everything you can see and touch. The superposition has not gone anywhere. It has only been hidden by the noise of the world paying attention. And here, at the edge of sleep, something interesting happens. The mind begins to loosen its grip on certainty. The self, which spent all day being one definite thing, begins to spread a little, to hold more than one possibility at once, to become something less resolved. This is not a quantum mechanical process in the technical sense. The brain is warm and wet and dense with molecular noise, and its superpositions, if they exist at all, collapse in femtoseconds. But as an analogy, as a way of understanding what it feels like to be a mind releasing its grip on the definite, there is something in it that feels true. The particle before measurement does not choose. It does not commit. It holds every possibility open with a kind of mathematical patience that has no anxiety in it, no urgency, no need to know. It simply is. Everything it could be, all at once, in the quiet arithmetic of the wave function. And then something asks, and it becomes one thing, and the moment passes. But before the asking, there is this, the superposition, vast and still and unhurried, containing everything and settling nothing, patient as the dark between stars. If you are still awake, that is fine. If you drifted somewhere in the middle, that is fine too. The ideas were here, and they will still be here when you come back to them, in whatever form they took as they passed through the edge of sleep and became something else, something softer, less defined, more your own. The universe, at its deepest level, prefers to hold its options open. It does not rush to decide. Perhaps tonight you do not need to either. And so we leave it there. The day is already distant. Somewhere behind you, the equations are still running, patient linear, unhurried, and every particle in everything is still, in its quiet way, everything it could be. Drift now, if you are ready. Sleep well.